this talk, we are going to present the RIS modeling, design and characterization activities that have been carried out in the framework of the RISE-6G project. I'm Raffaele Del Rico from CLAT, and I was leader of all package 3 in RISE-6G, where all these activities were carried out with University of Nottingham, Greener Wave, CNRS, CNIT, Aalborg University, Chalmers, NEC, NKUA, Orange, and TEAM. So, in a nutshell, the three objectives that we have. First one was to provide an electromagnetic RIS model and a system-level abstraction. Second one was to design, prototype, and characterize the RIS and the control logic for the proof of concept. The third one, to characterize and model the RIS-empowered reconfigurable radio channel. What concerns the first objective, we developed an end-to-end impedance model of meta-surface element and was validated on practical design and mapped also on system-level MIMO communication model. This was also extended in the end-to-end electromagnetic compliant mutual coupling aware channel model to practical scattering environment. This is the so-called RIS. We also developed some tools with hybrid analytical and numerical model of the RIS that were proven to be valid for reflecting RIS and transmitting RIS. Also, we proposed some resonant model to catch the resonant behavior of some unit cell that can be provided by the project. And finally, also was a specific FTD model that was also provided to simulate the RIS. So just to give an insight on the first part, is that validate this impedance model that started from one of the first work from University of Nottingham and CNRS that represented the full channel with the transmitter and the receiver with the RIS as dipoles with some specific charges. So everything is represented, the end-to-end transfer functions is represented by the impedance, and the most important part of this equation is the ZSS, which is the active impedance that catch all the mutual coupling effect, the characteristics of unit cell, and this ZRIS that is actually the impedance that represents what we can impose on the unit cell to make it reconfigurable. And we extended this on the classical scattering matrix representation. In order to validate this model, we consider some practical design. Here, for instance, a practical design of unit cell based on pin diode, and we run different simulation with the 0 degrees, the 100 degrees state, and the multiple simulation. What we want to show is that the model is able to catch the full characteristic of the unit cell or even the RIS with respect to the full wave. Here it's an example where we mainly show that the phase shift of the end-to-end impedance model with respect to the global matrix or also the full wave simulation catch in a quite well good way the 180 degree shift that we want to have, and the difference in dB is very low between the model and the full wave simulation that could be below minus 60 dBs. In the framework of the RISE-6G project, we developed a number of different RIS technologies that were investigated and provided by different partners. So, first family is the one based on pin diode, where they were K-band in RIS, in the reflecting mode, in transmitting or in transmitting and reflecting mode, but also in the S-band. Another one is based on RF switch and on MEMS technology in the S-band. Also, the variety of technology was investigated for 5.2 GHz RIS and also in the K-band, and we went up to higher band in D band by investigating some other technologies very different from the previous one, based on 30 nanometer silicon germanium BSIMOS process that is able to create a unit cell that can change amplitude and phase of the the response of the cell. So here an example of unit cell that was provided by Greenaway, that is basically a patch with the two parasitic resonator PH and PV for corresponding for horizontal and vertical polarization that are connected with the pin diode, and by changing the electrical length of the parasitic resonator, we can change its resonance frequency and can tune the multi-coupling between the resonant mode of the parasitic resonator and the patch. This translates in a phase shift, phase difference of 100 degrees. So this actually operates the 1-bit phase quantization with low losses around -2. These unit cells were packaged together to have a large RIS or 40 by 40 unit cell that were used for channel measurement and also for the proof of. This is another example of pin diode technology that operates in the 27 from 31 GHz, and there is a RIS that is able to operate both in transmitting mode using 2-bit phase quantization and in reflecting mode by using 1-bit phase quantization. Here, well, it's an example of how the unit cell operate in the reflecting mode, giving the 180 degrees shift, or in the transmitting mode with 4 states of phase corresponding to the 2 bits. And this was actually realized in the mission anechoic chamber, proving the ability to steer towards the desired angle on a range from -60 to 60. Another one is provided by NEC, is a reflector array of patch antennas 5.3 GHz, which is connected which uses some RF switch technology to commutate towards different length of lines, and this actually allows to have a different phase distribution. And also what is interesting in the design that we can switch the RF on load that actually make the unit cell work in absorbing mode, so we can have a reconfigurable shape of the RIS. This was also measured in anechoic chamber, proving its capability to reach different steering angle with the maximum scanning of ±60 degrees. Also provided by Orange is based on a reflector array with varactor. The varactor is actually able to provide a very precise phase shift with more than, of course, the 1 or 2 bits that we have seen before. And by changing the varactor, tension of the varactor, where we implement a different phase distribution that allows to easily manipulate the pattern of the RIS. So, for what concerns the RIS environment sound and modeling, besides the series model that we described before, we also had some random coupling model. We developed a preliminary DA code for 2D environments, and we had quite a number of measurements based on transmitting RIS, multiple reflecting RIS and transmitting RIS measurement to investigate multipath components, and also measurement in reverberation chamber. What is interesting here in this measurement campaign that for the first time we went beyond the state of the art by using different RIS at the same time, both in transmitting and reflecting mode. And the transmitting one is basically operating as a sort of 10 base station, the reflecting as a reflector, and we change the different phase configuration. And what we want to show here is the multipath, how they are distributed in distance, so in delay, and angle of arrival. This angle of arrival estimation was possible thanks to a virtual array and UV site. So here we show how with the transmitting RIS we can highlight the direct line of sight. And when we don't have the line of sight, well, what we can do is to use the reflecting RIS to activate some new paths that is clearly well identified in amplitude, in distance, and in angle, of course. And this kind of data that have been used then for evaluation of localization properties and localization algorithm employed. And these measurements were also used to evaluate and validate some path loss model based on radar equation of the sum of the different unit cell contribution. Also, with respect to the RIS model, that is an extension of the end-to-end impedance model that represents the scatter as a bunch of dipoles with some specific loads. This was used for the evaluation of and the optimization of, for instance, the sum rate, verified thanks to the measurement, showing that the direct path measured and the one simulated or reproduced by the model are very close, less than 1 dB approximation and accuracy. Okay, so in conclusion, what we had as a main outcome of our package 3 is the evaluation of different RIS technologies and their performance, which are also available sort of lookup table that have been used for the definition of the band of interest. The RIS and electromagnetic channel models were validated on practical design and with a specific measurement campaign, and there was an output for the system level studies and also different prototypes that have been now put for the demo. If you are interested in more details on this work, there are 4 deliverables then that have been provided and publicly available, and in particular the last one are on the model and the RIS prototype for the PoCs.